All right, we're back. Everything's working. Yay. Okay. Is that a sad, hard boiled egg in a plastic cup? Oh my God. Oh my God. Like, what penitentiary did you get that from? That just seems awful. The scrambled eggs must be awful if it's just like, I'm gonna put this like egg in this plastic cup and eat this. But if they mess up a hard boiled egg, that's like a level of like horribleness that can't really be met. All right, so which carbon is negative? Four, and that got to be orange. Which carbon is positive? Five. How many double bonds are going to be in my product? Two. One from the diene, and then one from the dienophile since it's an alkyne. So we're going to have our stock double bond, 1, 2, 3, 4, that we always have between carbon 2 and carbon 3. 5, 6. And we're going to have a double bond between carbon 5 and carbon 6, because I can only react with one of the double bonds from the alkyne. All right, so that means we have nitro group, bromine, no wedges and dashes, right? Just flat. Methyl group coming off of carbon 3, methoxy and methyl, same side or opposite sides? Same side. Wedgie, wedgie.
I was asked if you have to be able to draw and interpret both the caged three-dimensional structure of a bicyclic product and the flat structure.
This for the cyclic dienes, if you're gonna draw like kind of the caged like three-dimensional structure, or the other like with the wedges and dashes. If you're on an exam that you could write stuff, I would not specify. I just be like, give me the product. I would suss out which one was which. Like whatever you drew, I could figure out if it was right or not. So that'd be fine. There's like one or two homework questions I think that are like draw the product with wedges and dashes, as opposed to trying to draw the KG structure. So just make sure you read the instructions, because I usually get a couple questions that are like, it keeps saying it's wrong and I know it's right. And I'm like, look at the instructions, dog. Wedges and dashes. And they're like, oh, my bad. But yeah, other than that, like however you were to draw it, I would take if it was right. Yeah, so there's but like so for this next one is where you have to worry about like, are you drawing the three-dimensional like structure or not? Right. So okay, for this next one, which one is negative? Which carbon? Four again. Which one is positive? It's still going to be five, right? Because the electron withdrawing group is bonded to carbon six, which means the other carbon is positive. So now, how many rings should my product have? It should have three. So it's a cyclic diene, so we're going to have this, right? But also our our dienophile is also part of a ring, right? So that's going to make another ring. So here we're going to have our carbonyl wants to be straight down, right? It wants to be endo. So I've got 1, 2, 3, 4. So I make a 5-membered ring. Right? Hmm? You don't like it?
I was asked if the carbonyl group was really straight down from the ring.
It is, right? Pretty straight down. Right? like I will cut you some slack, right? As long as it's, I don't know, in the downward direction, right? As long as it's not like up where these hydrogens are, right? I'm fine, right? I understand it's not going to be like perfectly 100% straight down, but as long as you have conveyed enough that it is clear that it is axial as opposed to equatorial, right? And not in like that gray area of like, the mythical accitorial, none of the above kind of thing, I'm fine. So it wouldn't have to be perfect. Can I do it in the 2D? I can do it in the 2D. So here's the ring that we make. Harry Potter that up. And I guess for just comparison's sake, right, so you can see them side by side, so it might make more sense since I have itty bitty screen. Hmm?
A student said they thought the flat structure was way more complicated.
Yeah, it is more because you just have more you have to keep track of, right? Like, is it a wedge or a dash? The thing that people, when they try to draw it the 2D way, mess up the most is they'll put the electron withdrawing group on a wedge, which puts it on the same side as the bridge, which makes it exo. Like, that is the thing that when people are like, I'm going to do this, is they screw up all the time. So far, so good? All right. Which carbon is negative? Carbon 1, right? Sulfurs on carbon 2 can only push to the edge of the double bond that it's on. So this carbon is negative. Which carbon is positive? 6. Figure I needed to change it up because it's been 5 for like the last like 7 examples. Mix it up a little bit. Thankfully, as it's drawn, these two things want to bond together. Like as it's drawn, right? Carbon 1 wants to end up bonded to carbon 6 because negative wants to be bonded to positive. So it's a 5-membered ring. It's cyclopentadiene. So we have the single carbon pointy bit going on. Right, and now we have our carbon 5 and 6. Our nitro groups, our electron withdrawing group, it wants to be endo, so it has to be straight down. Right, and then that's going to mean that the ethyl group is also going to be straight down because it's on the same side as the nitro. And then the methyl group is going to be like up and at an angle. And then we've got methyl group on carbon 1, ethyl group on carbon 4, sulfur on carbon 2.
I was asked if the sulfur on carbon 2 was pointing up or in plane with the double bond.
It's not up. I did maybe a bad job. I was trying to get it around the arrow, right? And it's kind of like it's flat coming off of that double bond, but it's kind of hard to like accurately draw, right? So again, if you were drawing these like on an exam, as long as you were like, as long as you tried to make it look like it was flat, I'd let it slide. But like if you were like, doop de doop de doo, look at this, like that's like a horrific bond angle that's not right. I'd be like, it's a little rough. But as long as you like put forth a good effort, I'd be like, I could see how that's kind of in the same plane as the double bond. I understand that we are not art majors. We all want to be employed after school. So, like, I understand. So as long as I can like kind of see that you're like trying to meet me most of the way there, that one's really hard to draw, I think. If it was on carbon 3, I think it's easier to draw, but on carbon 2, it's just not great. I mean, again, I'm sure I could give this to like a freshman art student. They'd be like, "Oh, look at the perspective, blah blah," and I'm like, "Cool, cool." So it's like, so if I tell you to draw stuff, you can make it pretty. I can. Excellent. Come with me. Let's go. Let's go. Let's try to make this happen. You can be my understudy. Or even better, like I could just stay home and I could call them and then tell them what to draw and they could come in and draw it. They're young, they won't get COVID. It'll be fine. I was gonna say they won't get cancer, like that too, but they won't get COVID. It'll be fine. Where's your professor? Well, he just has a little avatar that comes in every day. All right, which carbon is negative? Should be carbon 4, right? So there's the electron donating group on carbon 1 is pushing electrons to 4, and the group on carbon 3 is pushing electrons to carbon 4. So they're working together to make carbon 4 negative. Which carbon is positive? 6. So now we're going to have to flip one of these two over. The easy one to flip over is clearly the dienophile. There's way less to draw, right? So these are going to react like this, right? Right, so carbon 4 wants to be bonded to carbon 6 in the end. Right, we're going to put a double bond here. So now, again, since we have a double bond there, we just have to get our nitrile and our ethyl group on that double bond, kind of in the same plane, right? There's no up or down here because it's coming off a double bond. Feeling good? No? Okay. That was indifference. I couldn't tell if it was indifference or like no. Indifference we can deal with. It's fine. It's fine.
I was asked how you determine the position of the groups on carbons 5 and carbon 6.
So like on 5 and 6 in the bottom example, right? Since there's a double bond there, they're just kind of in the same plane as the double bond, right? So, right, they're not up or down, right? So those are flat. The one above it, the electron withdrawing group right here, right? That is you need that group to be straight down. So that's the group that you kind of do everything based off of it. So you look at that and you say, this goes straight down. And then you say, okay, what's on the same side as it? Well, this ethyl group. So that ethyl group also has to be straight down because the rules of if it's on the same side of the dienophile in the starting material, it has to be on the same side of the ring in the product. So you're saying, I know this group has to be straight down. So you put that straight down in your product, and then you fill all your other groups from your dienophile in relative to that group being straight down. So like the first thing you do is just be like, identify my electron withdrawing group, make it down, and then fill everything in right out. You're like, this is on the same side, so it's down. This is on opposite side, so it's up a little bit. Does that make more sense? Okie doke. So hopefully that is enough examples for the time being. We feel good. All right, we're indifferent. I'll take indifference. It's fine. Indifference is not people like curled up in a ball, rocking and crying. So we'll take that. Take that. So we said that we made bicyclic compounds when we were doing reactions with cyclic dienes, right? Our products, those little cage structures, they're bicyclic compounds. There are three types of bicyclic compounds that I want to kind of introduce to you, right? There are spiro compounds. So spirocyclic compounds are two rings that are sharing a single carbon. Like, I wish it was easier to get to the purple color so I could, rep my boy Spiro the Dragon, but Spyro the Dragon, just like give him a little love. Yes, just make it purple. But guaranteed in the YouTube video of this, there will be a Spyro at this point, 100%. All right, so you're just sharing. You have the two rings, and they just only join at one position, right? They only come together at one spot. That's the Spyro compound. And this last one is really fugly. Let's try again. There we go. Right. So they just share one spot. Calm down, marine science. Not everything's a fish. They're all just. It's a big fish. It's a little fish. It's a fish with a square tail. Like, calm down. Calm down. Deep breaths. Deep breaths. All right. So you have spirocyclic compounds. Two rings share one carbon. You have fused bicyclic compounds. Two rings share two adjacent carbons. So these are kind of things we've drawn a lot before, right? So if you remember from organic one, you don't, I know. I like to say it like you do, right? Decalin, two six-membered rings stuck together, right? So you have two rings, or you can easily see two rings, and they are sharing two carbons that are on adjacent carbons. That makes them fuse. You've just taken two different rings and then fused them together to make this. Right? And then the last type is what we were getting when we were doing the Diaz-Alder reactions with cyclic dienes. These are called bridged. So these are two rings that share two non-adjacent carbons. Right. So right here and here are the carbons that are shared. And the two rings are like, here's this 5-membered ring, right? So that's one ring. The other ring is this 6-membered ring there, right? So you've got two rings, the 5-membered ring in red, the 6-membered ring in green, and they're sharing two non-adjacent carbons. If you draw this flat, right? Not worrying about stereochemistry right now. Right, you can see I have the big 6-membered ring that goes around the outside, and then a smaller 5-membered ring inside. Right, so we've got, here's my 5-membered ring. Here's my 6-membered ring. Right, so 2 rings, and they're sharing carbons that aren't beside each other. Those are bridged bicyclic structures. That got ugly as well. We'll do it this way. Right, so here's a 1 6-membered ring. Here's that 6-membered ring, and then you have the 6-membered ring that goes around the outside. Now, it's not only limited to the structures that we can make from our Diaz-Alder reactions, right? You could have, they're slightly harder to draw. Try that again. Right, I have a big 5-membered ring around the outside within a 4-membered ring inside. Right, so you could say like, oh, here's a 4-membered ring, and then here's a 5-membered ring. Reasonable? So those are the types. So now let's learn how to name like simple kind of unsubstituted versions of them. If you look at the slides, there's a whole section on substituted versions of them. We're not going to worry about that. So first you need to add the prefix for the type of bicyclic compound. And there are three, of course, there are 3 types of bicyclic compounds, so there are only 2 prefixes. Spiro for spirocyclic compounds, and then bicyclo, and that covers both fused and bridged. Oh, my brain turned off. So you need to stick in your prefix, right? So that's step 1. Step 2. So you need to determine the total number of carbons in both rings, right? That is your parent hydrocarbon. Step 3 is count and put numbers in brackets. I'm going to show you how to do that. That's the hard part. And I could write out all the rules, or I could just show you. It makes more sense if I show you. So you need to put the prefix in. So you need to say if you're a spirocyclic structure, or if you're fused or bridged. Pick your right prefix. Count the total number of carbons that make up the 2 rings. That's going to tell you what your parent hydrocarbon is, right? Hexane, heptane, octane, that kind of deal. And then we got to throw in some brackets and put in some numbers. And I'm going to show you how to put in the numbers now. So is that a spirocyclic structure, or is it bridged or fused? Spiro. 2 carbon, two rings, 1 carbon is spiro. Now we're going to put some brackets in. This is where I'm going to put the numbers when I count. How many carbons are there total in this structure? 7. So it's going to be spiro bracket heptane. Okay? Now, for the numbers, right, you count from the shared carbon back to the shared carbon. So you go, okay, 1, 2, 3, 4. So it's 4 to get back to the shared carbon. So this is 4. Then you put a dot, and then you count the other side, 1, 2. So this is spiro 4, 2 heptane.
The question was, why dots instead of commas? We always use commas between numbers in the past.
That was the rules I made. I don't know. Again, as I've said before, I simply live comfortably beneath the rules, and I communicate them to you. At no point has like chemistry ever got me on the phone and been like, yo, period or comma here. They've never asked my opinion. So, periods, right? So here, what I want to point out is Spiro only has has two numbers in the bracket. Right, so if you know it's Spiro and you put your bracket, you know you're only going to have two numbers. Right? You always list your numbers from largest to smallest. So they're always in descending order. So it's going to be 4, period 2. So we know this isn't Spiro. Is this fused or bridged? Fused. So as soon as you know it's fused or bridged, you know that your prefix is bicyclo. Bracket. How many carbons total are there in this structure? 8. Octane. So we're doing the same thing. We're counting shared carbon to shared carbon. So 1, 2, 3, 4. 1, 2. And now the last number is 0. There are no carbons between those two shared carbons when you're fused, right? So this is going to be 4, and it's going to be green for some reason, 2, 0. Okay? The 0 is how you know it's fused. Right? Bicyclo always has 3 numbers in the bracket. So if you have bicyclo as your prefix, you have to have 3 numbers in your bracket, and if it's fused, one of those numbers is 0. Right? This is bridged, right? So again, prefix is bicyclo, bracket. How many carbons are in this? 7. So this is going to be heptane. 1, 2, 3, 4, 5, 6, 7. And then shared carbon to shared carbon, it's 1, 2, 1, 2, 1. So it's going to be 2, 2, 1. It not being 0 is how you know it's bridged. Let's do a couple structure to name, and then we'll do a couple that are named to structure. And again, to help the marine science people, there you go. It really crystallizes it now. It's like, oh, they're all just fish. Sorry, there you go. It's a hatfish. There you go. There you go. Marine science, the only major where you're like, my life goal is to be eaten by Shamu. It's like the pinnacle of marine science degree. What do you eat when you grew up? Shamu kibble. It's like, woohoo. Okay, so first one here, bicyclo or spiro as a prefix. Bicyclo, how many carbons? Octane. And then shared to shared. What do we got? 222. So for this one, spiro or bicyclo? Bicyclo again. How many total carbons? Should be 8 again. Shared carbon. Seems like 3, 2, 1 to me. 1, 2, 3. 1, 2, 1. So 3, 2, 1.
I was asked if it matters what order you put the numbers in the bracket.
The order of the numbers does matter. You need to go from the largest number to the smallest number. So it should be like 3, 2, 1, 2, 1, 0. You should always be working your way down from the largest to the smallest. Bicyclo, hexane, 3, 1, 0 seems good. So we're going shared carbon, 1, 2, 3, 1, and then no carbons in between the two shared carbons. So for all the bicyclos, a little trick is if you add up the numbers in the bracket, it's always 2 less than the total number of carbons. Right? The first one was octane. The numbers in the bracket add up to 6. The next one is octane. The numbers in the bracket add up to 6. This one's hexane. The numbers in the bracket add up to 4. Right? Because you're never counting your shared carbons. So you're always short 2 carbons in your numbers, in your bracket. So if you look at it and you're like, do I have the right number of, if you're sure about the total number of carbons, but you're not sure about your numbering in your bracket, you can always just check and go like, okay, is 6 2 less than 8? Yes, it is. Thank you, Sesame Street. And then you're like, okay, I'm pretty sure that's right. So that's always a quick way you can check. Is to just do some kindergarten math.
Student, but kindergarten math is the hardest math.
Again, you have fingers and toes. You can do this. I have full faith in you. Just, take your exam in sandals and you'll be like, sweet, I have all of my counting tools at my disposal. All right. So this last one, is it going to be Spiro or Bicyclo? Spiro. It's going to be green, apparently. I only get two numbers. What is my total number of carbons here? Octane again. We're going to pretend it fit in that little space I gave it beside it. And then what are my numbers? 4, 3. Here, when it's spiro, you're always one short. So when the prefix is spiro, the numbers in the bracket add up to be one less than your total number of carbons, right? Because you just aren't counting your shared carbon. Reasonable? So a way you can think about doing this is like you're doing the worst activity book you ever did on a road trip. All right? You're playing connect the dots. So you got to, if you're bicyclo, you start with two carbons, right? So I have two dots. The 0 tells me there's no carbons between those two dots in one direction. So I just get to connect the dots, right? The 3 tells me I have to put three carbons between my two shared carbons in another direction. So I can go 1, 2, 3. The 4 tells me I have to put four carbons between the two dots. 1, 2, 3, 4. And there's my structure. Right? Like if I was better at this, like when you were done, you'd like see a sailboat, but I'm not that good. You're like, oh, it's a sailboat. Oh, this is great. I don't have that kind of skill here. Not like off the top of my head. And I don't have that kind of time to commit to your exam. All right, so same thing, right? You know you're starting with two dots. The 1 tells you that you've got one carbon between your two carbons, right? So I'm going to have 1. Another direction, I'm going to have 1. And in the other direction, I'm going to have 3. 1, 2, 3. Oops. I made it sound so easy, then I lost the ability to count. Again, you can only get so much. And if you don't want to draw it like this, you can also go like, this was a little harder to draw like this, but
I was asked if there was a correct direction to draw the rings as you make your structure.
no, if you kind of put them in the same direction, as long as like you can clearly see them, yeah, it's fine. Why are you doing that? And the trick about adding them up and knowing how many numbers off they are, that's how I'm getting the parent hydrocarbons. I'm putting the numbers in and then adding them up and being like, add 2. That's how many carbons this is. So at Spiro, you're starting out with just one carbon, right? And the 2 says you have two carbons to get back to it. And the 5 says you have 5 carbons to get back. Right? 1, 2, 3, 4, 5. 1, 2. Bicyclo, 2 dots. 1, 1, 2, 3. We did it right that time. 4, 1, 2, 3, 4. Hmm? I can draw it like that. And who could really do this? My art student avatar. Like there'd be shading, there'd be depth. This is the one that's gonna be. Yeah, that one. One, two, three, four. Yeah, but my one's a little sketch. I will admit that wholeheartedly. Mm, there we go. It's a little clearer. My art student avatar would make you feel something with that. You'd be like, oh, I don't know why, but it's so haunting. Hmm? Uh, could be both. Uh, secret thing. Chemdra has a bunch of bicyclo uh, templates, so I can just click and then I can pick one of them and click, and it will just draw it for me, perfectly proportioned and everything. So I can do either structure and then give you a bunch of names where I screw up the numbers and the orders of the numbers and stuff, or I could give you the name and then give you a bunch of different structures relatively easily for you to then have to pick out the structure. So if you feel good about all this stuff we did today, which was just basically a giant review and then some naming, there's 2 minutes left. There's no point in doing anything new. So we will start basically aromatic nomenclature on Monday.